Now we want to pick up where we left off last class and take a look at how, in this case, energy passes through the community. Again, we're going to use the food chain idea, recognizing that food chains really aren't the structure of the ecosystem. It's a food web, but you can pick pathways through that web, which would be food chains, and they're elucidative to, are helpful in understanding the limited flow over a limited area, so you can see things simply. Consequently, we're going to take a look at how energy would flow through a particular food chain, through a particular pathway. Let me get the PowerPoint up, I think. All right. So here's that picture we ended up last time with the food web, pointing out, of course, that the low will go on. Okay, pointing out, of course, that I'll draw them all here, that what we have here is a complex network of food chains that are interlocking and interwoven together to form sort of a fabric that's much stronger than individual fibers, if you want to think of it in a metaphor. As a result, ecosystems or communities are much stronger because they have this interlocking web-like network, which is really a weave of various potential food chains. And there's the diagram we ended up with last time, which we drew a whole bunch of the connections. I should have pointed out that these are the different trophic levels. Here's the producer, here's a primary consumer, these are secondary consumers, tertiary consumers, and you can see how the feeding relationships all interweave together. Okay. Well, we were talking about matter passing through the food chain there, and we realized that atoms don't degrade when they're used to make molecules, and consequently, you can recycle matter. Okay. But energy is different. We talked about the second law of thermodynamics. Let me get into the next picture here. Okay, we talked about the second law of thermodynamics. We pointed out that as energy is used for any kind of productive purpose, it degrades to heat. And therefore, once it's degraded to heat, it's not useful to go back and produce organized types of chemical reactions. Heat is really the essence of disorganization. And so energy is a one pass-through system. As it degrades to heat, it's not recyclable. A lot of students seem to forget that. And I get on essay questions and so forth where people talk about recycling energy, but you can't do. Because we get it from the sun predominantly. It comes in new every day, but as it's used, it degrades to heat, which is what keeps the heat, the world warm, and in some cases, as we're seeing now, maybe too warm. And your body metabolism is creating heat as you metabolize your food, break down the chemical energy in the food and use it to run your body, and the waste heat doesn't disappear, it converts to heat in the process. Okay. And so energy isn't recycled, it's a one pass-through system. It still, however, is transferred from one trophic level to the next through feeding relationships. The energy that you get to run your metabolism comes as chemical energy in the food that we eat, as do all organisms. Okay. Only the sun can get the energy from outside the physical environment, or from outside the physical environment, and convert it into accessible chemical forms that the rest of the biological system will use. And so let's use a diagram here, again, the food chain diagram. We'll start here with the sun, which is the source of energy for a biological system. And of course, it goes to the producers, PRs for producers, predominantly plants. The producers then convert that sunlight into chemical energy. They, through photosynthesis, take sunlight and carbon dioxide and water vapor and converts it into sugars. And sugars are complex biological molecules that have lots of energy in them. Sugar's energy food because it has lots of chemical bonds that release lots of energy when they're broken, right? And so all life uses sugar as their primary energy source, which ultimately goes back for almost all organisms except a few bacteria to sunlight. Then the next trophic level would be the primary consumers. They eat the producers, and the energy that they get is energy that was stored as the chemical energy in the molecules of the producers that they eat. So they digest that food, they break down those big molecules, and the energy that was represented by the chemical bonds holding those molecules together is released to allow them to go ahead and use it for their metabolism. And then the secondary consumers eat the primary consumers, and again, they're getting their energy in terms of chemical energy stored in the biological materials that the primary consumers are made of. And then finally, we go to the tertiary consumers all the way out the food chain. And they, in turn, all these various levels provide food for the decomposers. Here's where the difference is, because when matter was there, our decomposers then released all the raw materials that were recycled back up to the producer base. But in this case, each one of these steps, energy is lost. It's degraded. It's converted to heat as it's used. And consequently, if we were to go ahead and take a look at where the energy is going here, here's a symbol for heat. We would see that at each transfer, when the primary consumers heat the producers, some of that energy is degraded to heat. And when the primary consumers are fed on by secondary consumers, some of the energy that was chemical energy in the food is released as heat during the metabolism of the secondary consumers, and so forth down the line. And in fact, the most heat is released by the decomposers because they feed at all trophic levels. So the total amount of heat represented by the feeding of the decomposers is, at least in our diagram, 4 times as much as the heat released by a single feeding relationship between 2 different trophic levels. Not surprisingly then, the bulk of the energy in an ecosystem is tied up in the decomposer base because they're fed by the raw materials from all the different trophic levels. That making sense to you?
Yeah.
All right, let me ask a question here then. Why don't you store wet hay in a barn?
It's gonna rot.
No, it's not the problem. I mean, it will rot eventually, but that's not what you're worried about.
It's not decomposing or decaying or rotting that is the problem?
Nope.
Mold?
Nope, that's rotting. What happens during rotting?
The decomposers are basically decomposing the material.
What do they release?
You say, what are they releasing?
Yeah.
Heat?
Heat.
Oh, I see.
Barn fires. When there's water for the decomposers to get active, they release enough heat that could cause the hay to catch on fire. So at Pierce, for example, we have hay, but it's not in a barn. It's in an open area outside, underneath a roof, but it's open on the sides, right there by the beginning to entrance to the farm, so that if there is a barn fire, you're not going to burn down the barn. Okay, so heat is released. And the compost heat, the operating temperature in the container of a compost is about 140 degrees. That's as hot as the hottest hot water setting on your water heater. Okay, so heat is the energy that's being released as all these biological activities are going on. It's the second law of thermodynamics coming into play. So by the time a biological molecule has passed, say, from one trophic level to the next, or the energy from the producers has passed through these trophic levels, by the time it gets here, it's been all degraded to heat. And that heat is not recyclable. So energy is a one pass through. Now we're lucky, the sun's going to continue to shine for another few billion years, so we're not in danger of having it stop. Okay, but it's not infinite. Okay. The sun puts out only so much energy, and that's it. On our latitude, it's about 160 watts a square meter per day. Half the day is night, so that now we're not getting any. If you just take the daytime hours, it's a little bit more because it's concentrated during those times. But it's a finite amount, right? And part of the problem is we've stored up a lot of sunlight with fossil fuels that have tucked it away as geological reservoirs, reserves. And we've burned up maybe 100 million years worth of fossil fuels in 100 years. And not surprisingly, that there's a very rapid input of new energy and new materials into the atmosphere. It's changing the dynamics of the Earth because it's been tucked away and stored for 100 million years rather than 100 years. So heat is heat energy is disorganization, pure and simple. Now, the questions we might ask then is just how efficient are various organisms at passing on their energy from one level to the next. In other words, if a primary consumer is eating a producer, how much of the chemical energy in the producer becomes part of the primary consumer, and how much of it is actually released as heat during the metabolic processes, okay? That would be a measure of efficiency. The total amount of energy consumed minus the amount that was lost to heat is what's left over for the organism to use to build its molecular structure. Remember that the bonds that hold together these biomolecules that make up the living systems are actually stored energy. It takes energy to make those bonds. And so if we take a look at efficiencies, they vary drastically. Some organisms are much more efficient at converting food energy into their molecular structure than others. And it varies maybe from as little as a couple of percent up to maybe 50% for different species. Right? And so when we're talking about a generic concept, how much of the energy in the producer base is transferred to become part of the primary consumers? We'd have to take an average of the various organisms at that trophic level to be able to make a general model. Okay? Now, one of the things that we need to concern ourselves with here is the two different categories of vertebrates. Vertebrates would be animals like ourselves that have backbones that live on land, that are pretty much the animals that we think of. So we should realize that there's a lot of animals, or at least single-celled animals and so forth, like the protozoans that aren't vertebrates, don't have a backbone. But if we start thinking about vertebrates, there are two general categories that we can identify. Well, they used to call them warm-blooded and cold-blooded. And the idea behind that is warm-blooded organisms generate their own body heat, maintain a constant body temperature. And cold-blooded organisms depend on their heat and the temperature of their body by absorbing heat energy from the environment, their surroundings. Right? But this is no longer a valid term because warm-blooded and cold-blooded really is non-descriptive. Okay? The terms now are endotherms and exotherms. Exo means they get their heat from outside the body. Endotherms mean, like us, that they generate heat through their own metabolism. Okay. Now, the reason the difference is warm-blooded implies that you have a warm body. There's a lot of cold animals that don't generate their own heat that are very warm. The yucca night lizard, for example, which is a common desert lizard out here, has an average body temperature of 107 degrees Fahrenheit. Like that, almost a lethal temperature for us. So you wouldn't want to call it cold-blooded by any standards, even though it gets its energy by absorbing it from the environment that's outside of its body. So the term that we use now would be ectotherm and exotherm and endotherm, excuse me. Endo means into or inside of, and exo means outside, external. And so exotherms basically absorb their heat from the environment, generally from sunlight. And endotherms generated by the breakdown of food during their metabolism. So we maintain a rather constant body temperature by regulating the amount of food we're digesting, basically, to keep the temperatures consistent. And one of the questions that biologists have is why would what are the advantages, if there are any, of being endothermic? There's not very many types of organisms that are. The only two that exist here are birds and mammals. All other organisms are exothermic. Now, there are some organisms, like the great white shark and so forth, whose body temperature is maintained at a temperature slightly below the ambient environment, but they're not full-blooded or full-on endotherms. And so there's some question about how they're doing that. They seem to retain a little bit of their metabolic energy, metabolic heat. But for the most part, it's the temperature of their surrounding water, for example, that determines what kind of body temperature they're going to have. And so we might ask ourselves, what is the difference between the two that might provide some kind of selective advantage for one or the other? If you take a look at us, we're exothermic.
Wait, no.
Go ahead.
We're endothermic.
You're right. I'm sorry. I beg your pardon. So,
unless you're a lizard and you're not telling me.
Yeah, I'm a lizard, that's for sure. I'm struggling to make sure I don't say ectothermic because that's a little bit different temperature. And exothermic, ectothermic are different things. So I didn't want to get sloppy there, so I got sloppy somewhere else. Yeah, we're endotherms, and birds are. Now that means that it's like our engine's always on. We're always on a rather high rev to keep that temperature going. What that does is mean us that we're not very efficient organisms. We require an awful lot of food to maintain that constant body temperature. Okay, we got to eat every day, or we should eat every day anyway. If we don't eat too many days, we'll run out of food and our body will die. Okay? So that you might ask the question, why in the world would this warm-blooded condition, this endothermic condition, have evolved? It seems to have a disadvantage. You require a huge amount of food on a constant basis. Right? Well, that's a good question. I've got some ideas on it that are my own, but I can't claim that I've read a whole lot of scholarly works from scientists that are answering that question, though it's probably out there somewhere. But when you think about it, chemical reactions are temperature dependent, okay? And the general rule of thumb is for biological reactions, or basically organic chemical reactions of all types. If you if you increase the temperature at which the reaction is going on, individual molecules are moving faster and further, therefore are encountering each other more frequently, and the rates of reaction double for about every 10 degrees centigrade temperature increase you have. Okay? And so at a high body temperature, you've got aggressive chemical reactions going on in a coordinated fashion, so the metabolism is running pretty quickly, right? The constant body temperature means then that you can develop a body chemistry that has some dependable temperature requirements so that all the various chemical reactions can fit together better. If your temperature is constantly going up and down, some reactions respond to temperature different than others, and getting a coordinated ballet of chemical reactions that we call life, it becomes a little bit more problematic. And so I think we sacrifice efficiency for the sake of having a constant temperature situation so that the biochemical reactions that have to coordinate with each other can develop to go on at just the right amounts and just the right rates to give us the most efficient coordination. Okay? But we're paying a price for it. The price is that we have to have a constant input of fuel. It's like leaving your car on idle all the time. Can't shut down. So you're going to use a lot more fuel than if you can turn it off. Now, the exothermic organisms that get their energy from the environment, they release some metabolic heat as well, but they just dump it into the environment. So they don't require a constant supply of fuel to maintain this idling condition, shall we say. To give you some comparison, some mammals, especially the small ones whose metabolism is running really fast, are birds for the same way. They have to eat constantly, maybe even their body weight every day just to keep their engine going. Right? A hummingbird will starve to death in 3 hours if it doesn't get any food. It has to go into a starvation state in the evening to be able to sleep in the evening. Okay, that's one of the problems. If a hummingbird gets trapped on your porch, can't get to a flower for a couple of hours, you come back and it's dead, starved to death because its metabolism is going so fast. Okay. On the other hand, we take a look at an exothermic organism like, say, a snake or a crocodile, reptiles. You know, a crocodile may only have to feed 50 times a year. And it can sometimes go a year without feeding. Okay, it just metabolism slows down and it doesn't have much of a demand for energy, sluggish and so forth. Right? The same thing for snakes, and for that matter, reptiles in general. I was out in my backyard working on projects I got there, and I have these little lizards that the California Anos that are my buddies. They run around in my garden and feed stuff. When I'm watching this one guy that staked out a territory right near where I do some work, so I'm getting familiar with him. He's running around all day long looking. He only gets to eat something maybe once every other day. He catches something. That's enough to keep his metabolism going. Eats insects. Catches. He may be feeding secretly at night when I'm not looking at him, but he's not even, getting very lucky in terms of his hunting strategies. But that's enough to keep him going. So there's a trade-off here. It takes a lot more energy to support a bunch of endotherms than the same amount of ectotherms. Now, if we take, actually we ought to develop this a little bit more because we live here in Southern California, where a lot of the organisms that we come with are exothermic. Okay, the trick there is that they maintain a body temperature that's fairly constant, but they do so through behavioral mechanisms. Let's think of you go out to the desert and you see a chuckwalla. Right, a chuckwalla is a pretty big lizard. It's maybe a foot and a half long, got a big fleshy tail. It's usually extremely black or very dark green. Okay? And if you watch this thing during the day, you see that it has a rather interesting pattern of behavior. they'll spend the evening wedged into some crack underneath the rock where they're protected. Because as the night falls in the desert, sometimes it gets pretty chilly there, their body temperature drops. And the body temperature drops, the rates of chemical reactions slow down, and they become sluggish and torpid and perhaps unable even to move at the coldest parts of the night at a rate that's fast enough to do anything. So they best find some place where they just can sleep it off, so to speak, their metabolism goes down. Come the morning, light comes out, still cold, but they'll crawl out onto a rock. Now the chuckwalla is black or dark green because those colors absorb light effectively. The light colors reflect most of the light. The dark colors, black especially, tends to absorb all the light that hits it. So it's going to spend some time there sitting on this rock or whatever its den is, usually a rock in the desert, oriented perpendicular to the rays of the sun coming up in the east. That way its body is absorbing the maximum amount of light, the light's converting to heat, and it's slowly heating up. Okay? In addition to that, it dilates the capillary blood vessels right near underneath the skin, so it diverts a lot of blood to flow underneath the skin to pick up that heat that the skin's absorbing and transfer it to the rest of the body in the body's core and so forth. So a half an hour and the temperature, body temperature of that chuckwalla is warmed up to 80 or 90 degrees. Whatever its normal body temperature would be. I don't know right offhand. And now it starts out on the feeding forages. One of the good things is that by now the insects are coming out, but they're exothermic as well. And as a result, they have to warm up before they can get really active. So the chuckwalla warms up a little bit earlier, comes out and can gobble up some insects that are not able to move very quickly because they haven't warmed up yet. Right? But the problem with exotherms is that they can get too hot. You can absorb too much heat. So here's the chuckwalla. He's walking around. He's following, if you look at him, a definite pathway that he's sort of staked out. It's his territory. So he'll walk from here to that place, to this rock, to that brush, so forth. And about 10 o'clock in the morning, he's been absorbing light to the point where his body's too hot. And he could die of heat prostration because those chemical reactions can start going so fast that their coordination disappears. Right? So now he's got to find some shade. And the shade is a critical resource. It's not like just a comfort level. If he doesn't get out of the shade, he's going to die because he's going to have heat prostration. These biochemical reactions are going to be going on too fast and too uncoordinated. Remember, the hotter you are, the warmer you are, the less coordination you have, the more entropy you've got. So you'll find out that on his pathway, there's a bush right there. At the right time of the day, he's got a bush that he'll sit underneath in the shade, cool off a little bit, adjust himself so his long axis is parallel with the sun rays, so he's not absorbing very much, and release some body heat for a half an hour or so until his body temperature drops down to the point where it's ideal. Then he'll get up and he'll move around again for an hour or so. His body temperature goes up. By the time he gets over to here in his little orbit of wanderings, there's a little rock ledge there that he'll then crawl under. He uses that same rock ledge every day to get out of the sun and cool off a little bit. And so all day long, this chuckwalla is migrating around this pathway that's fixed, uses the same pathway every day. And just at the time his body's overheating, he's got staked out some kind of refuge to become cool and lose heat and keep from overheating. And every time he needs heat, there's a place where he can display to the sun and pick some heat up. So actually regulating his body temperature pretty accurately through behavioral mechanisms to absorb external energy. That makes sense?
Yeah.
Now you got a problem here because a lot of people think the desert's dead. And maybe they'll go and take a bush that looks like it's dead and then run a motorcycle over it or something or kill it or hate it. But in so doing, that might be an island of shade for a number of different types of animals. Now, only humans go out in the desert in the middle of the day. The rest of the animals have found some way to not have to do so. So you kill that creosote bush or some kind of dead-looking plant of some type, and there might be 100 organisms, from insects to vertebrates, that depend on that plant for shade at a critical time during the day. And when they get there and it's not there, their body's going to overheat, and you can kill a whole lot of organisms by simply removing a plant or turning a rock into a different position, things like that. So the desert is a low productivity ecosystem, but consequently it's pretty delicate. Right? So you don't want to go out there and wham it away and kill it. It takes a long time for things to heal as well. So the chuckwalla will do fine as long as you leave it alone and it has its migratory pathways. But when you get in there and disrupt it, you might have some serious problems with it. And this is not a unique organism in that regard. Take a look at just about any of the desert reptiles. They have a similar kind of situation. Even non-desert organisms. You go take a look at a crocodile, right? In the morning, the crocodile will get up, still sluggish. It's got water temperature. His blood's the temperature of water he's been sleeping in. So he'll crawl out on the shore, orient himself broadside to the incoming sun, and just plop down there and start to sun himself. You notice the back of the crocodile has all these little knobs on them, little bony projections sticking up. What do you think they're for?
More surface area to release heat if it gets too hot.
Yeah, they're more surface area to absorb sunlight. They stick up rather than just be a flat skin. So he's got much more surface area for light to fall on, and he dilates the blood vessels so that blood is flowing directly underneath the skin, doing a nice little job there of picking up the heat that the skin's absorbing. So that's an extra benefit for absorbing heat. Well, eventually he'll get up to his core temperature that he wants, and then he'll go swimming around looking for food, and that'll cause him to cool. Okay? When it gets too cool, he'll get back out on the beach and expose himself to the sun to reheat his body, warm up the blood again. Later in the day, some may be more intense, so you'll find that they actually adjust their angle so that they get just the right amount of sunlight and heat, not too much and not too little. So in the early morning, they'll be square onto the sun. 2 o'clock in the afternoon, they may have an angle there at 30 or 40 degrees to the sun's rays, so the degree of absorption just gives them the amount of heat that they need, not doesn't result in overheating. Very, very effective ways of regulating heat. So it's not like organisms that aren't endothermic, somehow or another unregulated. They have very exquisite methods of controlling their body temperature, but that depends on an interesting relationship with the external environment from which they get their energy. Right, so you want to be careful here. The desert's not dead, and you've got to take into account the needs of the organisms there before you start developing things or chopping stuff down or doing whatever kind of mayhem you want to do when you go camping. Okay, now, excuse me. If we average these together, one more thing we ought to say. Because exotherms don't require as much energy, we can also think of them as being much more metabolically efficient, okay, because they only need to feed a few times a year in some cases. That means that for a given amount of food, you can support a lot more exotherms than endotherms. Okay? So a given amount of food can only support so many mammals because they're burning it up fast. That same amount of food might be able to produce support 2 to 3 times as many reptiles, or as much biomass of reptiles, because they don't require as much food, right? And so one of the things that paleontologists especially are looking at, those are people that study fossils, questions like, were the dinosaurs warm-blooded or cold-blooded? Were they ectothermic or endothermic? Exothermic or endothermic? Well, one of the things you can look at is predator-prey relationships. If your predators are warm-blooded, I'm going to use those terms because they're stuck, but are endothermic, then you're going to have a lot of prey for a rather few predators, right? If on the other hand your predators are exothermic, then you can have a lot more predators relative to the amount of prey because each predator doesn't require as much food. And so by looking at predator-prey ratios in the fossil record, you can get some idea whether or not populations are exothermic or endothermic. There is, though, one confounding problem here when you're looking at dinosaurs, because all organisms, when they eat and digest food, release some heat. The endotherms regulate that to give them a constant body heat, but even reptiles and so forth release heat when they digest their food, they just lose it. But if you have an organism the size of a brontosaurus, 6 times bigger than an elephant, it doesn't lose heat very well. The heat has to be released from the surface of the organism, right? But the volume of the organism is huge, and so you can generate a lot of heat within that big volume, and there's not enough surface area of the animal for the heat to escape to the environment, and it'll be trapped. It's called inertial endothermism. They may not be deliberately doing it, but their internal body temperature may be very warm because they're generating more heat than can escape out the limited skin area. The bigger the animal, the greater the volume of the animal relative to its surface area. Little tiny animals can cool off quick because they got lots of surface area, not much volume. But when you get up to an elephant or something like that, that don't have air conditioners, then they're likely to have very hot blood or hot body temperature without any metabolic process deliberately doing that. And then their rates of biochemical reactions will be much more rapid than you might expect in that case, right? Okay, so if we average this all together, we wanted to look generically at a food, the big picture. We ask ourselves, well, what is the average amount of efficiency at transferring energy from one trophic level to another? The general trend is to think it's about 10%. In other words, about 90% of the energy that's produced, that is contained in, say, the producer base, is lost either as undigested food through the waste stream or as heat, okay? And about 10% is available in terms of the biomass of the producers that are then available to the primary consumers. And similarly across up the food chain. So the estimate is, that are generally used for calculations would be 10% efficiency. 90% of the energy is lost at each trophic level. Now, that's quite a profound loss, okay? So you have primary producers here, but most of the energy that they possess is lost to heat as they become food for the primary consumers. So you're only going to be able to support about 1/10 of the volume or the mass of primary consumers. Or let me rephrase it this way. You're going to need 10 times the mass of primary consumers in terms of producers to support 1/10 the weight of primary consumers, right? So you get a big drop off in the total amount of biomass. Biomass, B-I-O-M-A-S-S, is simply the mass of living material, the total weight, if you will, of all the life in that area. Right? And at each trophic level, then, the average is about 10% gets transferred. So the biomass of the secondary consumers would be about 1/10 the biomass of the primary consumers. And the biomass of the primary consumers would be 1/10 the mass of the producers. Right? You always got to have more prey than predator. And for most organisms, about 1 to 10, though it varies from one organism to another. Well, then think of your poor tertiary consumer sitting out here at the end of the food delivery system. Okay? By the time the food gets to you, it's pretty well been used up. Only a small part of it, 10% of 10%, 10%, 10% gets to you. Okay? So let's say we had a ton of producer organisms, ton of grass. How many tons of primary consumer could that support?
You have 1 ton of grass, you said?
No, yeah, a ton of grass.
1/10 of a ton of grass.
Which is what?
1/10 of a ton. Is a ton 2,000 pounds?
In the English system, a ton is 2,000 pounds. In the metric system, a ton is 1,000 kilograms, I believe.
Oh, okay. So then if you've got a 1/10 of 1,000 kilograms, 1/10 of 1,000 is 10? 100?
100, yeah.
Okay.
But it's good math.
I need more coffee.
Yeah, they don't do this in calculus. No fractions. But... All right, so let's say 1,000, just keep it in simple units. 1,000 pounds, 1,000 kilograms of producers could support 100 kilograms of primary consumers. How many kilograms of secondary consumers could that support?
10.
10. And how many kilograms of tertiary consumers?
1.
1. So you got huge amounts of producers that can support a rather small population biomass of tertiary consumers. That's why you don't have extremely long food chains. In very, very high productivity, primary productivity ecosystems, you might get a quaternary consumer level, a 5th level, but almost never. Because by the time the energy gets out here, precious little gets out enough to support a viable population of tertiary consumers. Now, this is a really critical point. That means that tertiary consumers, the gnarliest, biggest predators that everybody looks at as being the pinnacle of evolution, are the most vulnerable of all the organisms in an environment. They are the first to go whenever there's any kind of environmental stress, because they're so precariously balanced at the end here of a rather limited food delivery system. Okay? And so one of the measures of environmental problems is if the top level predators disappear, things are in deep trouble. Okay? And we're going to take a look at what happens when that occurs, because there have been bounty programs and so forth put in place to try to limit and get rid of the wolves and stuff like that. And not surprisingly, it's had a rather significant ecological impact. Okay, so the energy transfer along a food chain is about 1/10 at each trophic level. That means if you take question, yeah?
Yeah, so we talked about kind of how much biomass could be supported along the food chain, but what about decomposers?
Well, they get the biggest biomass of all because they get things from every part of the food chain. So the bulk, if you go to the Sierras, right, and you're walking along the forest floor, that's really not the forest floor. That's maybe 30 feet of yet to be decayed or partially decayed organic material that's fallen from trees and so forth before you get down to bedrock. And all that is energy available to the decomposers, but not to any of the other components of the ecosystem, right? So in any ecosystem, it's the decomposers that have the bulk of the energy. Fair enough?
Yeah, thanks.
Okay. Now, you've heard people say, when we take a look ecologically at the various organisms, if you're going to have a big population, it's going to have to feed lower on the food chain where the energy is more available. Okay. If you're going to have a population of very big animals, they're going to have to feed lower on the food chain to be able to support their biomass. This is why the biggest animals are not carnivores. They're not tertiary consumers. The biggest animals in an ecosystem generally are primary consumers. All these great big giant dinosaurs were basically eating plants. If you take a look at a lion, that's a pretty big predator, but it's eating zebras and things like that are bigger than it is. Right? So when it comes right down to it, the big whales are plankton feeders. The carnivore whales are like the biggest one's a killer whale, and they're much smaller as a consequence. And so if you have a big demand for energy, either because there's particular species demands the kind of food that's energy rich, or you have population numbers that mean that requires a huge amount of energy to support that population, they're going to feed lower on the food chain. Okay. Now, ecologically, this is real. People have extrapolated this, however, to human values. People say it's eating meat is somehow or another unnatural because if you're eating meat, you're a tertiary consumer, or at least a secondary consumer, and you don't have enough energy to support a big population of secondary consumers. So as world population increases, people are finding it more and more difficult to have any kind of animal protein in their diet. And they're becoming more and more dependent on producer bases as populations of all big consumers are doing. But that's been proposed as a solution to the world population problem. Let's just have everybody eat less meat, more closer to the producer base. Well, this is a stress situation. It's not some kind of novel solution. Human beings, let's be honest here, did not evolve simply to eat plants. And not that there's anything wrong with it, but to suggest that rather than control reproductive enthusiasm, it's better to let everybody just overproduce, and then everybody will eat something low on the food chain, and we'll take all the land in the entire world and turn it into agricultural land, is not a solution either. Okay? But it is something that's inevitable. As world population grows, it's becoming, you can't support it with the limited amount of animal protein that can be produced, whether you're doing it artificially or it's coming out of nature. If you've got a cow, you got to feed it an awful lot of grain to get the cow to build, and they're going to turn that into meat that's much more demanding than eating the grain that you would use to feed the cow in the first place. So there's pressure then to feed lower on the food chain, shall we say, as population gets bigger. But I think that's a consequence of the problem and not a solution. Okay, is that making sense? That gets me in trouble a lot, but I think the realities here are the realities. Okay. Well, there's an awful lot to be said then from just taking a look at this simple food chain model. and seeing what happens to energy. We figured out some social impacts, some biological impacts. We can understand why certain types of animals occur where, why prey are always bigger than populations are always bigger than predator populations. The exo and endothermic relationships and so forth. There's been a lot of to look at by simply examining energy flow through an ecosystem. So far, we cool. Any questions on this?
No, I don't think so.
Okay. Now, see if I missed anything. Let's see what the next slide is. All right, so the energy transfer here we talked about. Let's say we have 1,000 kilograms of producers. That could support 10%, 100 kilograms of consumers, primary consumers, which would support 10 kilograms, which is 10% of 100 is 10 kilograms, and then 1 kilogram of tertiary consumers. Okay, so it's a big giant loss at each step. The further out the food chain you are, the smaller the populations can be. The bigger the organism, the fewer number of individuals that can support. It's all about biomass, the mass of biological organisms, which is what requires food to support. All right. I want to talk here about a concept that's a little bit difficult. No, I don't want to say that because I don't want to scare anybody. It's a subtle idea that requires a little bit of, I want to get this out of here. I know how to do that, I think. That requires a little bit of work to get your mind around it fully. And that's the problem, not the problem, but the consequence of ecological niche. Most people call it ecological niche, but it's not a niche. It's spelled N-I-C-H-E, niche, which is a French word. But I feel weird saying niche all the time, so I'm probably going to call it a niche. But you can go either way. And the ecological niche is a concept that's at first thought of pretty simple. I'm going to introduce it very briefly here, and then we're going to use the next lecture to develop it fully because it's a subtle idea. A lot of people think that there's a sort of the ecosystem has a bunch of cubby holes in it, and every species fits into a cubby hole, and that's its ecological niche. You know, what it eats, what it needs to have for nesting, and all that kind of stuff. But it's a much more subtle concept than that. So we want to develop the concept of ecological niche, which is basically the entire life structure of an organism. It includes everything about the organism, not just what it eats and where it nests and what kind of temperature it requires, how much light it requires. It entails all the interactions it has with other species and the degree that those interactions are required. You don't often see that, but every tree in the forest, for example, would not survive if it wasn't for a network of fungi that are growing underneath the ground that are parasitizing the trees, but are breaking down nutrients and making them available to trees. You eliminate those kind of things that you don't even see, and all of a sudden you have a cascade effect in the entire ecosystem. So the ecological niche is a very expansive concept that contains a huge number of components, not just the obvious ones that you can see. And so we want to develop this idea because one of the questions that ecologists have is, do the species evolve and define the niche that they have, or are the niches there which define the species, what things can do to survive and therefore determine what species you get. It's an interesting concept that's being still debated. Species ecological niche then is a pretty all-inclusive concept. It's best measured too. Modern ecologists today are really working in mathematical modeling. They model an ecosystem as a multidimensional vector space. Take linear algebra, for those of you gone past calculus, to look at that. And they're basically talking about every ecological niche is the vector space in a multidimensional space that has any number of components to it. Each component would be a dimension in that vector space. So ecological, here's a species. When you look at it from its niche structure, it may be it may have a 500 dimension vector space that you have to work with, which is what linear algebra does. Don't worry if that didn't make any sense to you. It's not critical, but I'll sort of introduce you to that simply because it's neat. And all I want you to do is realize we're going to start thinking expansively about ecological niche, not just, you know, where something lives or what kind of nesting materials it needs and so forth. So write that down. Ecological niche is what we're going to talk about. And it's rather critical because you can't really understand the development of evolution of individual organisms or of ecosystems without understanding niche structure. And so it's a very active topic in ecology. All right, no questions? Okay, then ecological niche is what we're going to talk about next time, and we'll see you then.